Folks hear me okay? There, the mics are up. Well, good evening and Happy New Year.
Happy New Year!
So, welcome to the January meeting of the Royal Astronomical Society. Maybe a new face for some of you. Dave Chisholm, I'm your new meeting chair. You've stuck with me for a couple of years.
Yay!
Anyways, we'll see how this goes. It may be a little bit rocky tonight, but as I get a little more comfortable with this, we'll move on. So let's take a look at what we've got on tonight's program. So we've got, obviously myself, and Simon's going to be talking to us about the science of Venus. And we've got Jim doing Understanding Astronomical Filters. We have some observations, announcements, and door prizes. That's our schedule for tonight.
Wow.
We did really well in 2019, lots of new members. And we have 5 new members already this year, so welcome to the Royal Astronomical Society. I'm going to continue in this role for the next little while. I tend to use these observations for my outreach, so I don't want to be creating the same thing twice. So we'll continue with the Ottawa skies. Let's see what's happening in January. First thing, clouds. Okay, in terms of the moon phases, January the 10th is the full wolf moon, and these are the moon phases for the month of January. We have the Quadrids meteor shower tonight.
Right.
That's cloudy.
Right.
Enjoy. I've added this is a sunrise, sunset times, if you can ever see the sun. But I've added this to my presentation so you can just sort of see how the sunrise and set are progressing through the month. Mercury is not visible. Venus is visible after sunset. Mars is visible just before sunrise. Jupiter is not visible. Saturn visible early evening, first half month. It's setting really, really early now, so good luck. Uranus is visible all night, and Neptune is visible the first part of the night. And there is our cartoon for the month.
What's with the wire?
This is an airplane that can fly across and drop candies. Unfortunately, they didn't leave us any candies, so this is sometimes set up here, and we're not allowed to do that, so we'll just have to look through the wires. Just pretend it's those new satellites they're setting up there. Let's just get excuses for that.
At least you don't have the line here.
Yeah. So, members in the news. Simon has been, his paper has been accepted for the Earth Science Reviews. So, he's going to He is talking about Venus tonight, but it will not be in the same detail as this. But he said he will talk about some of the aspects of his paper at a later meeting. So I'm going to turn it over to Simon now for his presentation. Thank you, Simon.
Sorry, the screen's not working there, so I'm going to be pushing that.
Oh, that's okay.
All right. Now, you may recall, this wasn't that long ago, in the second half of last year, I gave presentations at this podium on the status of scientific inquiry regarding the moon and regarding Mercury. And both of those are actually up on my website, which you can actually get through the RASC Ottawa webpage. Drop down the Education tab, and it'll lead you to Planetary Geology, and that'll lead you to my presentations page on my website. Now, in light of the speed of scientific advance, I want to focus on the questions of that planetary scientists are asking themselves today about the bodies that comprise our solar system, which is why I'm doing a bit of a mini-series on this. Now, given the breadth of scientific endeavor today, which is a reflection of the pressure to publish to obtain funding, whatever the discipline, doesn't have to be astronomy for this to kick in, I've opted to avoid the detailed stuff and to focus just on the big picture questions such as why is Mercury such a weird planet, and let's not worry about all the scratch marks. Now tonight I'd like to turn the spotlight on Venus, and Venus is a very different kettle of fish from the Moon and Mercury, certainly from our perspective. It's one of those cases where the science is really not advancing at a significant pace. In fact, from my perspective, Venus science seems to be bogged down in dispute and controversy, as opposed to advancing towards enlightenment. Now, as amateur astronomers, when we think about terrestrial planets, we tend to be strongly influenced by what we know, what we can see on Mars, the Moon, and Mercury. However, all three are visible to us in white light, and a pretty good resolution of that. Basically, all we have to do is look, even if we're looking at the internet. Venus, on the other hand, is very different. It's shrouded by a deep, dense atmosphere made of carbon dioxide, CO2, in cloud form, of course. And hence, the best way to see the ground on Venus is using radar. And therein lies the fundamental problem for Venusian science. The last probe that was sent to Venus with the explicit aim of mapping the bedrock surface using radar, and a few other wavelengths as well, was NASA's Magellan probe of the early 1990s. And what this means is that scientists today are studying Venusian geology with the same old data set that they've been using for the last 30 years. They've got nothing new. Now, while better than what we had before Magellan, these data are pretty coarse in terms of resolution. For example, about 120 to 300 meters per pixel, depending on which way you look. So a lot of necessary detail is just simply not resolvable. You can't see the same kind of detail you can see on the Moon, Mars, or Mercury. Nevertheless, a great deal has been accomplished. However, Venus has not been at the center of attention for the world's national space agencies for a long time. It's clearly a poor relation compared with Mars and the Moon, both scientifically and politically. That's important when it comes to funding. Now, one of the consequences of this is that the Venusian science community tends to be relatively small and relatively isolated. From my biased point of view, and I emphasize my biases, from my biased point of view, Venusian science is dominated by physicists and chemists, and it suffers from a lack of cross-fertilization with geologists, especially those with field experience, people who've actually been out and seen the rocks and seen what rocks do. But as I say, I'm biased. However, recently there's something new in the air. Groups of scientists are beginning to push more forcefully for the funding of new science missions to Venus, principally driven by two politically popular imperatives: climate change and exoplanets and the search for life outside of our solar system. Bedrock geology per se is currently seen as a secondary or even tertiary priority, though it won't be ignored altogether. So we'll look at what this means towards the end of the presentation. However, before we start thinking about where Venus science might possibly be going in the hopefully near future, we should take a moment to consider where we are today, what we think we know, and how we got there. Now, until quite recently, most of what we knew about Venus came from the data sent back by the Russian Venera mission and NASA's Magellan probe in the 1980s and the 1990s, respectively. In fact, with few exceptions, one of which was the Pioneer program, pretty much everything we know about the geology of Venus stems from these two missions. This is probably the most widely reproduced image from the Venera mission. The ground at the feet of the lander that only lasted for a couple of hours in the Venusian heat, more than 450 degrees centigrade at the surface, hot enough to melt lead, and obviously melt the electronics here as well. The slabby nature of the rock at the that was not what I wanted to do. This is what I wanted to do. The slabby nature of the rock, these slabs here and there and there and there, that slabby nature there was taken initially to represent thin lava flows. But there's a school of thought today that says, well, these actually might be ancient sediments, perhaps deposited in ancient water. Now this quintessential radar image. I say quintessential because it's been reproduced so many times. This quintessential radar image of the surface of Venus was captured by the Magellan mission. And it was processed by NASA to improve its communications value. What you see here are extensive extensive low-lying plains here, and then these volcanoes here with these extraordinarily exaggerated steep slopes. This image has over 20 times vertical exaggeration compared with the horizontal dimension. So this is actually not what Venus would look like if you could get down there and look at it. But the most important thing in this image is the general lack of visible impact craters. For various reasons, which I won't get into, they're all related to impact crater statistics across the solar system, especially the moon, and on Venus itself. This lack of impact craters on Venus has been taken to mean that Venus has been resurfaced by relatively recent lava flows on a planetary scale, thereby covering and hiding any trace of its early impact history. Think resurfacing of the street we live on by the municipality in order to cover up and hide the potholes. It's the same kind of thing. Now, originally it was suggested that a catastrophic event occurred sometime during the last billion years, some say around about 500 million years ago, whereby older crust sank into an overheated, internally melted planetary mantle that in turn sent new magma to the surface to form new volcanic crust, thus some localized volcanoes such as the two you see there. However, there's always a however in there. More recent thinking, still based on impact crater statistics, so essentially using the same data but processing it differently, now raises the possibility that this renewal of the planetary surface must have occurred piecemeal and over an extended time frame in a non-catastrophic, steady-state fashion. So, complete opposite of the previously generally accepted hypothesis. Now, it turns out that there are all sorts of geophysical reasons related to the internal nature of the planetary mantle that provide potential support for this non-catastrophic, steady-state view. So the number one geological question that planetary scientists are still asking themselves about Venus is how and when did the surface we see today form? And that's a pretty fundamental question for an entire planet. Now, the next fundamental geological question for Venus is highly controversial, but it remains unresolved. And it is, are the major features that mark the surface due to internal or external processes? Did it happen from inside or outside? Now, by major features, I mean a variety of generally round plateaus, donut-shaped features, holes, that measure hundreds to thousands of kilometers across and occur all over the planet. You can see many of them here. It's a patchwork blotchiness, but that one there, which is really obvious, and that's called Artemis. It's 2,000 kilometers across. So you can see the size of these other patches and blotches. They're in the same order of magnitude. Now, by internal processes, which technically is referred to as endogenic, coming from inside, I mean hot, buoyant, planetary interior material that I just refer to here. Yes, I refer to here as convecting. That material rises up and deforms the planetary surface, according to one perspective. By external processes, technically referred to as exogenic, from outside, I mean impacts by really large bodies, bolides they call them, asteroids we would call them. And these are coming in, of course, from space, way outside of the planet. Now this is another pretty fundamental question to be asking about an entire planet. Surely we should be able to tell the difference between these two possibilities. The structures on the surface of Venus formed by things coming up from inside or coming in from outside. It doesn't get much more fundamental than that, does it? Well, we should be able to tell the difference. Maybe. Very good. So I'm going to invite you to try this visual test with me. This is a radar image of a crater on Venus. Here it is. about 100 kilometers across, just to give you a sense of size. What do you think? Is it of volcanic, internal, endogenic origin, or is it of impact, external, exogenic origin? Now, this thing here, the long run out of here in what looks to you to be white, it's about 600 kilometers long. And it certainly looks like something that's flowed outside of that round crater. But don't be fooled. It's not a volcanic lava flow. Let's take a closer look. If this round crater here is a volcanic crater, then where's the giant volcano? Remember, it's 100 kilometers across. Where's the giant volcano that it should be sitting on top of? Now, what are these short petal-like lobes? You see them here as well. Now they're very similar in texture to the rest of the periphery of the crater, even here. Same kind of texture, rough and rubbly. Now if you compare this crater, the one we've just been looking at, with another crater, this one over here, which is called Dickinson. The previous one was called Adams, but that doesn't really matter. It's about half the size of this one. The pictures are not the same scale. That's about 50 kilometers across. But it has those same petals and that same beautiful texture and a nicely developed rim. And actually something nice in a nice mound in the middle there, peak in the middle. And it's a very well established impact crater. So Adams, this one here, it turns out, is actually a well-known impact feature, and the long run-out is either impact ejecta went one way rather than in all directions, or it's impact melt. So the take-home message from this image here is that you really have to think about craters on Venus before jumping to conclusions about their origin. Now some scientists, in the minority mind you, have suggested that this is exactly the case with respect to many, if not most, of the supposedly volcanic features all over the Venusian surface. So let's take a look at why they think this. This pair of images here shows you an overhead and an oblique perspective view of domes, each probably in the order of 50 kilometers across. So each one of these would be about 50 kilometers in diameter. Now, these are thought to be unique to Venus. No one's actually seen anything quite like this on any other planet in our solar system. Now, note that the perspective view, again, has a dramatic vertical exaggeration, again, over 20 times. And that's what gives the false impression of these near vertical sides to these domes. They are called pancakes, but just like the ones you make, the sides are not standing about an inch above the pan. Now, the domes are classically interpreted as volcanoes, with the idea being that some of these things in the center have things that might look like they're volcanic craters. And the idea is that they're made of very stiff, or technically viscous magma, or, more recently, as some people have suggested, of piles of volcanic crystals. In other words, no magma at all, just the crystals popping out of the ground. In any event, they're assumed to be of internal endogenic origin. However, as pointed out by the dissident minority, primarily represented by the late Warren Hamilton, younger domes cut across older domes in a cookie-cutter fashion without any deformation of the older domes. Here's an example right here. This one here is cutting across that one, but this one hasn't been distorted at all by the arrival of the younger one. And geologically, this would be rather extraordinary if it were the case. Something pushing up from the interior of a planet, something thick and viscous, pushing against something that's already on the surface should distort both the planetary surface and the shape of the earlier feature. The earlier round feature shouldn't be round anymore. But this is not what we observe, as these images clearly show. So the dissident minority group says, well, where else in the solar system do we see large, round, cookie-cutter features? And then we'll be out for this. It's on impact crater terrain, such as the Moon or Mercury. This is the image we've just been looking at from Venus. And this is a set of craters from impact craters from the Moon. And if you look carefully, you can clearly see that the older crater here is cut through cookie-cutter fashion by the younger crater with no distortion. The same thing happens here. The younger crater cuts through the older crater with no distortion of the older crater. It's cookie-cutter. That's exactly what you'd expect from an externally derived exogenic impact phenomenon. So the descending minority then goes on to suggest that the Venusian features are in fact crystallized lava ponds that were produced by the heat of external exogenic impacts and not internal volcanism at all. So are they right? To be honest, I don't know. But they do ask a very valid question which the majority of workers working on Venus have simply ignored. Now this question of internal and external driving mechanisms also applies to the features that measure hundreds of thousands of kilometers across, apparently unique to Venus and referred to as coronae. Now this image here shows you what they look like and their general distribution all over the planet. So, this is a blow up of this area here, so you can clearly see these round features. They're obviously planetary scale. These are in the hundreds of thousands of kilometers across. And if you look at the rest of the planet, you can actually see lots of round features all over the place. I'm showing them in blue here, but they actually occur around places like this as well. So these are the famous corona that you may have heard of. Here we see a close-up of a corona feature, plus on the right, a cartoon of how it might have formed according to a model of internal endogenic convection. And the general idea is that the large mass of buoyant hot rock would have risen from within the planet, that's the convection part, domed up the planetary surface, that's showing it there. The hot stuff rising would have then cooled, and as it cooled, it would have become denser, and so it would have started sinking back away, and dragging some of the surface down with it, and leaving you with a dimple with a ring at the end of the day. And that's what they say you can see here. There's the large dimple, and that would be the ring. And the radiating spokes that you can see here, according to this model, those would likely represent vertical sheets of molten rock, called magmatic dikes for those that like these terms, injected into the upped dome and stretched crust. However, that minority dissenting group comes back with a dissenting view, and they say that many of these corona features actually look very much like large impact craters, with a central peak, an external rim with slump features around through here, and then ejector in a ring on the outside. In other words, they're not the result of, they are the result of external exogenic mechanisms, and not internally driven at all. They argue that if coronae were the product of rising mushy rocks from within the planet, then where they overlap, in other words, where they intersect each other, the younger coronae should distort the older ones. In short, the older coronae should no longer be round. But as you can see in these three images, this is not what we see on Venus, at least with some coronae. The coronae of in the first two images are numbered, such that 1 is the youngest impact. So there's 1 here, 4 is older. There's a huge difference in size, so we won't use those. But if you look at how 4 here, which is older, I didn't do that. I did not do that. Okay. That's the big bump. But you look at 4 and the younger 3, it's not really distorting the margin there. And you can say the same thing here. There's 9, and then 4 hits it, 5 hits it, and again there's no distortion. You might say, well, actually kind of weird. Let's go over and have a look at this. There's number 1, and it's cutting number 2, which is still perfectly circular, and it's cutting number 3, which is even older, and it's a perfect circle. And these two here, you can even bother to number these. Here's the older one, and there's the younger one coming through in perfect, pretty cookie-cutter fashion with no distortion. And this, the dissenting group argues, can only be achieved with externally driven impacts and large impacts of that. Now remember, what we just saw with respect to overlapping impact craters on the moon. There's our example hiding up here in the corner as an insect. Are they right about this? Does cookie cutter geometry automatically mean that these have to be impact features derived from outside of the planet? Are they right? Once again, I don't know. But yet again, they're asking a very valid question that the majority of workers continue to simply ignore. Now, internal or external processes, you know, this question was asked about the moon over 50 years ago, and we resolved it over 50 years ago. And yet we're dealing with the same kinds of observational data, and we still have two schools of thought. There is no middle ground. Okay, however, let's be very clear. Just because some important surface features might be generated by external processes, that doesn't automatically mean that the interior of the planet was not geologically active at all, and that it wasn't convecting at all. It's just a debate about how much of the surface features are internally and externally derived. So let's switch gears now and briefly look at the geology of Venus as a planet at the global scale. No more of this small scale 2,000 kilometer stuff. This global map of Venus distinguishes high ground in the pinks from low ground in the greens and especially the blues. The low ground, the blues and the greens there, is principally occupied by the lava plains that resurface the planet. However, and whenever that actually occurred, because we don't know. Some of the high ground, some of the pinks, is considered to represent the oldest rocks on Venus. They're called massifs, and they're actually referred to as crustal plateaus in case you ever come across this. These crustal plateaus have been the subject of much intensive research for the past 30 years, principally because it was thought that they held clues which might explain how the crustal plateaus themselves formed above convecting cells operating within the planet, within the early hot planet. One school of thought concluded that the crustal plateaus formed over rising plumes of hot material, hot rocks, while another school of thought arrived at the opposite conclusion. The same crustal plateaus formed over the top of sinking plumes of cold material. And they debated back and forth about what this might all mean. Anyway, the long and the short of it is, then a new school of thought concluded that neither hypothesis was valid and proposed that crustal plateaus were actually the product of truly massive asteroid collisions. And if this sounds to you like the internal, external, endogenic, exogenic debate all over again, you would be correct. However, I have to warn you that an entire school of thought suggests that in fact the interior of the planet was too dry and too stiff to convect at all. More controversy, but that's the topic for another day. And just as an aside, this talks about how these crustal plateaus formed and whether or not things were uplifted, coming up or going down and what have you, and even the evidence that people were looking at to run with this discussion. That's the subject of the paper that was just pointed out to you at the beginning of the session today. I could go on with more examples. Don't worry. I won't. But you know, in short, when it comes to even the broadest outlines of the geology of Venus, there's still a great deal we don't understand. How and when, and from inside or from outside. I haven't even touched on the detailed stuff, but that I will do another day, but we'll do it in a way that's generalized and more follow along. But there's more to Venus as a planet than bedrock geology, believe me. First to say this. And geophysical theories regarding its interior. More recently, the main feature of scientific interest has been its atmosphere and its climate. During the past 15 years, both NASA and the Japanese Space Agency, which is JAXA for short, they've sent probes to Venus into orbit around Venus specifically to investigate the atmosphere of Venus. Yes, good. JAXA's Akatsuki mission. Akatsuki apparently means dawn. It's focused on mapping the structure of the atmosphere, as well as the nature of its winds and clouds. And as this diagram summarizes some of the results, it looks kind of busy. Well, that's the nature of atmospheric science. It is very busy. I liken it to 3D chess, where even the chessboard is constantly moving and changing. And describing this would entail details that I don't think we want me to get into here. Certainly not tonight. NASA's now completed Venus Express mission also studied the Venusian atmosphere in great detail, but I'd like to just highlight one tangible finding that came out of that mission. One of the big questions that scientists have been asking about Venus for quite a long time, even before sending probes, Venus as a planet, that is whether it ever had significant quantities of water, surface water perhaps, maybe even oceans. And the evidence stems from comparing the deuterium-hydrogen ratios of Venus and the Earth. I don't have the time to get into that here. That again could be a topic for another day one day. But here's the important bit. If Venus was once wet, then how did it lose its water because it's now gone dry? The simple answer, which we've known for a long time, is that the solar wind emanating from the sun simply stripped away the hydrogen from the associated water, H2O, pull the hydrogen out from the oxygen in the atmosphere, and then let the solar wind strip out the lighter hydrogen and carry it off into space. But it would be carrying it away from the Venusian cloud tops. But Venus Express made an interesting discovery. It turns out that although Venus doesn't have much of a magnetic field to write home about, it does have a planet-wide electrical field in its cloud tops. And an electrical field far stronger than was previously thought probable. In a word, because I'm not a physicist, there's this electrical field because the electrons have been pulled away from the hydrogen proton, and as they've been pulled negative from positive at a distance from each other, that generates the electric potential, and there's your electrical field. That turns out to be quite a find because this electrical field can significantly accelerate the dissociation of water and speed up its loss to the solar wind, in addition to the effect of the solar wind on its own. So we seem to be getting an interesting answer to a major problem. So, what's my take-home message to you? Well, it's a question. Where does Venus science go from here? I mentioned at the beginning of this presentation that there is a serious move afoot to persuade NASA to mount a new mission to Venus. The group of scientists goes by the name of the Venus Exploration Analysis Group, or VEXAG for short. And if you're interested, there is a URL for them down there. And they're chartered by NASA's Solar System Exploration Division, so this does appear to be a serious initiative. Even its name, and a series of questions under the banner heading Unveiled, it even has a name. And it also has a series of questions under the banner heading of Unveiled Venus, why is Earth's sister planet so different? Interestingly, this is almost exactly the subtitle of my very first presentation to the RASC here that I made at this podium back in 2001. Now, if you pass the keywords in the questions listed here, and by doing so, there's the keywords there that I've passed. If you pass those keywords here, you can see where the VEXAG group is coming from and why this new initiative might, at last, have legs. In a nutshell, it's all about climate and climate evolution. How did Venus get the climate it has? In other words, climate change. Even though, as we've seen, our understanding of the geological evolution of Venus as a planet is muddled, riddled with more questions than answers about something as basic as whether Venusian geology evolved from the inside of the planet or the outside, from space. In addition, we're still very unclear about how the planet will resurface and when this happened, let alone its possible link to possible climate evolution. Imagine if you actually had catastrophic volcanism that covered the entire planet, you'd do something to the climate, probably something nasty. However, this VEXAG communications graphic gives the impression that the new mission would be intended to examine all of the scientific aspects of the geological and climate evolution of Venus. If you look, you can see everything from orbiting probes, actually looking down, using radar of course, to the surface, or looking into the atmosphere, or suborbital, in situ orbital sensing, the idea of descent probes going down through the atmosphere and measuring as they go, cloud level platforms, stay in the clouds, gliders that you're talking about, and then these landers down here, short-lived and long-lived, up to a year on the surface. And if you look here, they're jumping up to 2030. This is near term, 2020. That's this year. Hang on for a second. And they're talking about rovers and low altitude balloons. However, the reality is that space science today is inexorably wrapped up in mega funding. And mega funding is wrapped up in politics. And when science gets mixed up with politics, the scientific roadmap can get a little difficult to follow. So here's my last slide. Nonetheless, things become abundantly clear when you take a look at the 3 non-prioritized goals for this mission. Non-prioritized, if you've ever gone before a Treasury Board with a multi-million-dollar project proposal, the first thing you get asked if you put 3 goals forward is, well, what's your number 1 priority? Supposing we only fund one of them. You don't go in and say, well, you're not prioritized. That means you haven't thought through your application. But this is what's being presented. Again, look at the keywords in these goals. And the keywords are potential habitability, atmospheric, and even where surface is mentioned, it's coupled with atmosphere. And in fact, the reference to surface is in great part a proposal to examine the effects of the alteration of rocks, or weathering for those that like this, on the chemical evolution of the atmosphere. Now, I don't blame DEXAC. I very much doubt that bedrock geology or even the geological evolution of Venus as a planet would garner much serious funding in today's political climate. Climate change, on the other hand, has name recognition. And these days, that's the name of the game, even in science. As always, thanks for listening. If their hands up, I can't see you.
Maybe you can turn the lights up a bit, Chris?
Jim, I can just about make you out.
In the radar images that scientists are working from, we see light and dark shades. Do they distinguish different material types or just different textures? Like, what do they signify?
What Jim's asking is, you saw, especially that picture of Adam's crater there, you saw the white color. And there was other stuff that was sort of darker or grays. And he's asking, what does that actually really represent? And this is one of the reasons why I emphasized at the beginning that we look at the Moon, Mercury, and Mars in white light, and what you see is what you get. Whereas when you're looking with radar, you've got to have a completely different mindset. Radar is all about the nature of the reflection coming back at you. It's not white light coming back and coming back as red, coming back as blue, coming back as green. It's radar. Radar essentially, if I've got it right, is a wavelength, or they might choose different wavelengths, but they're looking at a wavelength at a time. It's how much did you get back? And that principally depends on 2 things. One is the roughness, in fact the granularity of the surface, and the other is the angle of the surface being hit. So if you're looking at something and you look at it to the left, and then look at it to the right, using radar, you may get a totally different picture. So one's got to be really careful about interpreting, oh look, all this white stuff here. Maybe that's all the same composition. No, it's probably a similar texture, but the composition could be varying dramatically.
Hi. I was wondering if the atmosphere, because it's so dense, could play a factor in some of these things. For example, there was a pancake-shaped lava things, because it's like at the bottom of some of our oceans, the pressure's so high that the lava comes up and kind of squashes it.
That's an excellent question. The question is what kind of role does a really thick, dense atmosphere play? After all, you're basically down on the surface of Venus with its dense atmosphere. The pressure there is about 100 times more than that at the air pressure at the surface here. And it is like being down in water. I don't know the exact depth down that it's equivalent to, but it's in the order of a kilometer or so. And the question is, well, does that have an effect on things at the surface, like, for example, the shape of pancake volcanoes? The answer is yes. But we don't know when any of this volcanism occurred. And we don't know when the atmosphere, if it was Earth-like to begin with, if it had water to begin with, we don't know when it would have changed. So, for example, if the major resurfacing of Venus had happened, let's say catastrophically, for the sake of argument, we don't know if it happened 4.5 billion years ago, or if it happened 500 million years ago. And we don't know exactly when these pancake-shaped volcanoes, for example, formed with respect to those lava plains. So the answer is yes, but we don't have enough detail to actually piece together even the time relationships, which is really strange, and this is why it's such a good question that you're asking. I should be at this microphone, shouldn't I? I think my voice carries reasonably well. It's really strange because there are scientific papers which have been through peer review, which call upon a dense atmosphere to explain the models that they're putting forward, and yet they have absolutely no evidence that the atmosphere was like that at the time that they're trying to model.
Simon,
Yes.
the crater atoms that it showed, so it shows a distinct kind of ejecta blanket around it, but then there's that 600 kilometer runoff. Could there be lava tubes under the surface there that have been fractured and then bubbled up, let the lava up, and it kind of settled where it is?
The problem with this is the resolution of these radar images. As I said, the resolution tends to be about 120 meters or 300 meters per pixel, depending on which way the radar is pointing, by the way, with respect to the orbit. And so we don't really have that kind of visual detail. There's no reason why there couldn't be. But I must admit that when we look at the moon and we can see, especially with those beautiful Japanese pictures from the Hayabusa probe, I think it was called, which was the most incredible high-resolution black and white images I think I've ever seen. And they managed to really image impact melt, much smaller scale than what might be proposed to add in the crater. And it was all pretty smooth stuff. So I really can't answer your question because A, we don't have the data, B, we don't actually have examples of this kind of scale on any of the planets that we can see in white light, and especially the moon where we can actually see in incredibly detailed resolution. I don't know.
One more question? Here?
This is a very basic question, which is, how can the study of Venus's atmosphere help scientists understand climate change here on Earth?
In a nutshell, they can't. The question is, sorry, I should repeat the question. The question is how can studying Venus's atmosphere help us understand the evolution of the Earth's atmosphere?
Right.
Or climate, if you will.
Yeah.
What happened on Venus is what's called a runaway greenhouse. Runaway greenhouse doesn't mean, oh, it's getting hot, and it's going to continue getting hotter. Runaway greenhouse means something very, very specific. All the surface water of the planet disappears, outwards. It goes out into space. And in fact, for a full runaway greenhouse, which is what happened on Venus, that the water from inside also would be cycling into the atmosphere, and it is also lost. So the entire planet has lost its water. We're not looking at that kind of climate evolution. So Venus is such an extreme version. Could we find some mechanisms that actually help us understand how the atmosphere may have evolved? Possibly. Like I was saying about the Venus Express discovery of the electrical field in the cloud tops of Venus. Don't know how that actually helps us understand how our climate is evolving today. Because we're at a much slower, much lower level. No, the truth of the matter is, and I'd probably get hung on court for saying this, the truth of the matter is there's nothing like a good exaggeration using something which is politically popular to try and drive forward a grant application.
Got it. Thank
On
you.
that cynical note.
Okay, this is different than the slides I have. There we go. Okay, it was a two-step one. Just so you know, we have an astrophotography workshop coming up with Paul Cloninger. I've taken his actual course, and it's absolutely awesome. And I'm sure this is going to be absolutely awesome as well. Price is much better than what I paid. It's free, it's open to members. Registration deadline is Sunday, so if you do want to come, please register. Email president@ottawa.rasc.ca to register by this Sunday, and you will get directions as to where the workshop is at. It's going to be 2 afternoons, January 11th and 25th, from 1 to 4 p.m. So president@ottawa.rasc.ca, and I know it will be an excellent workshop. Oh, we have some calendars still for sale. They'll be available at the table over here during the break.
Eat what?
No, they haven't been reduced yet. Maybe next one. Okay, we're going to be moving into the break. And during the break, come up and get your door prize ticket. I've added something new, though. I want folks to be thinking over the break. I'm having an Eminem challenge. Moon and Messier challenge. I'm going to be putting up 2 objects. These objects are from the Astronomy magazine, has these flashcard series. There's the flashcards for the moon, there's flashcards for Messier objects. So I'm going to be putting up 1 Messier object, 1 moon object. Certain people shouldn't be answering right away. You know what I'm talking about. So these are the 2 objects. Over the break, discuss among yourselves so you can figure out which ones they are. And we're going to be gathering back here about 25 after. So about 10 minutes for a break. And we're just reminded that the rest of the museum is closed at this time. Okay, thank you. Maybe we could keep the lights down, just down here a little bit so people can see the image. There, that's good.
Yes.
Use them, and then at a later date, I'm not sure if it's next month or the month after, I'll give the second half, which will talk about what the filters are that you should look into getting to use in your own kit, as well as some pointers on how to use them. So let's get started with part 1. We have here a lovely mountain scene. Very good color, nice contrast. Lots of nice detail in the image. This is kind of what we try to achieve when we're doing our astronomical observing or imaging. We want to get a nice, crisp image that clearly shows what it is we're looking at. Unfortunately, more often than not, there's something getting in the way of getting that perfect image. And this is where filters come in. Because filters can take what you don't want to see and make it darker so that you can now see the rest of the image with more clarity. And that can help with improving your contrast and sharpness. It can help to emphasize features that you want to see, one versus another. And it can also help you to see features that would otherwise not be visible because they're too dim.
Oh, okay.
So on the bottom right, I have a little schematic of what a filter looks like. It's very simple, really. There's a aluminum machined housing within which a flat piece of glass fits. And then this whole assembly screws on the end of your eyepiece or the nose piece of your camera, depending on what you're using. It's pretty straightforward. But the secret is in what that piece of glass is. So as I mentioned, the filter's purpose is to make darker in the image the wavelengths of light that you don't want to see. Doing this helps you to see the other parts of the scene more clearly, but it does not make them brighter. It only makes what you don't want to see darker. This is achieved using 2 different technologies. One is absorption of the wavelengths that you don't want to see, and the other is reflection. And some filters actually use a combination of both. So let me give you sort of an example. This isn't real images, these are simulated, but I'll give you an idea of what you can achieve using a filter, for example, when observing Mars. So this is a beautiful image presented from the Hubble telescope. lots of good contrast, good color. You can see, lots of detail in the clouds up here, on the night side, and then the polar cap, all clearly visible. Unfortunately, this is not what you see when you look through a telescope here on Earth. You see something that looks like this. I'm sure you all recognize this view of Mars. Well, this is where filters can help. By selecting a particular wavelength of light, for example, red, you can emphasize parts in that image so that you can see them more clearly. In this case, using a red filter really accentuates the contrast between the light and the dark features on the surface of the planet. Similarly, if you use a green filter, the contrast between light and dark isn't as intense, but you can see more fine details in the darker regions around in here. But it does subdue clouds and polar cap. To pull those features out, you need to use a blue filter to really emphasize the clouds and the ice caps. So this is just sort of an example of how applying filters to your planet observing can help you to see features more clearly. Moving on to filters for deep sky application. This, if you can believe it or not, is an image of the North American Nebula, taken from my backyard in downtown Ottawa with no filters applied. So you can just make out a Cygnus wall here. This is the Gulf of Mexico, Florida, and the rest of North America is up here. So indeed, I'm on the right target here. But if you add a filter to remove the light pollution, you can really pull out the contrast in the target. So areas that are dark, dusty areas appear dark. Areas that are bright, emission nebula are bright. You can really pull out those contrasts using a filter. So there are two basic types of filters. Those two types are based on the way in which they are blocking the light you don't want to see. The first type, they have a couple of different names. You can call them planetary filters. You can call them color filters. Some people call them Ratten filters, and I'll explain what that term means a little later. But basically, these are all filters that use absorption. The light that you don't want to see is being absorbed by the glass in the filter. The other type, some people call deep sky filters or nebula filters or light pollution filters. These are all terms describing the same type of filter. And they use the wave property of light, and I'll explain that in more detail later. But it's basically reflecting away the light that you don't want to see and allowing the light you want to see to pass through the filter. And I'll explain later how that works. So these are the two main types of filter. And of course, for every rule, there are exceptions. And I call these special filters. And they use a combination of both of these techniques to do special tasks, like observing the sun. Hydrogen alpha filters that you use for observing the sun, they use the same filter technologies, but applied in a different way for observing the sun. Similarly, if you have chromatic aberration in your refractor, there are filters you can get to help cut that down, especially designed for that purpose. Or filters for cutting out ultraviolet and infrared if you're using a camera. So there's specialty filters as well that use the same techniques, but I'm not going to talk about those for now. In this talk, I'll just talk about the two main types, planetary and nebula. If you have questions about those, I can answer them afterwards. So this is my skillfully crafted schematic of an absorption type filter. Essentially, you have the media here through which the light is passing, and I've sketched in here a desired wavelength, which is passing through the filter without any attenuation, and then the undesired wavelength that is getting attenuated as it passes through the filter media. Most absorption filters that you buy today are not glass that's infused with a dye. as suggest here, but they are gel infused with dye that's sandwiched between two pieces of glass. The reason they're made that way is because it's significantly cheaper than dyeing the whole glass plate. It also means that you probably shouldn't get your color filters wet, because if moisture gets in the ends, it will cause delamination. So just keep that in mind with color filters. So whether it's the glass itself that has the dye in it, or if it's the thin layer of gel in between, it's the material in the dye itself that's doing the absorbing. The actual molecules of the dye are such that particular wavelengths of light get absorbed and others do not. And this is sort of a recipe passed down through generations to figure out how to do this. And that's where this Rattan figure cuts in. Back in sort of the turn of the century, there's a fellow named Frederick Rattan. He was a British inventor. He started out as a teacher and he started getting into photography later on in his life. And he came up with a very systematic way of creating different colored filters. And he was able to sell this idea to companies to make filters that are standardized and are still even used today. They're used today because Eastman Kodak in 1912 bought this cookbook for filters from Frederick Rattan, and they still make them today. So if you see a color filter, I can back up to show you.
That's it.
Back up a little too far there.
Also.
There we go. See the numbers on the filters here? Number 8 yellow, number 12 yellow, 21 orange. Those are Rattan numbers. So those are the numbers that Frederick Rattan assigned to his systematic way of creating filters. And the actual spectral response of each of these filters correspond to the spectral response of the filters that he designed back at the turn of the century. And they're still made today in the same way. Still made for terrestrial photography, but now we use them for astronomy. So there's a little piece of history for it. The one thing about absorption type filters is that because of the technology being used, it's a little bit rough. You can't really finely choose the wavelengths that you let through and that you don't. So you end up with quite wide spectrum pass bands, and the wavelengths that you're trying to cut off, it's not really sharp, it's more of a gradual cutoff, and you'll see what I mean later when we look at some spectrums. So as a result, the performance of these filters aren't great for applications where you're trying to pick out very specific wavelengths, such as if you're trying to observe deep sky objects. So for planetary purposes, they do a good job. For deep sky, not so much. Which is why interference type filters were developed. So this is a schematic for an interference type filter. It's quite a bit more complicated than an absorption type, but I'll try to walk you through it. So it starts with a piece of clear glass upon which there are many, many layers of alternating materials applied. And these are on the order of a quarter of the thickness of the wavelength that you're trying to pass. So tiny, tiny layers. And they're put on using a process of ionizing the material and then misting, like a vapor, depositing on the glass blank. And there's hundreds to thousands of these layers alternating. And each layer has a different refraction index. As a result, as light passes through from one layer to another, at the boundary, some light is reflected, some light is transmitted through. Just like when you look at the surface of a swimming pool, you can see to the bottom of the pool, but you can also see a reflection of the sky. So it's this property of a boundary between two different materials that we get this reflection transmission behavior. So at every single interface, there is a reflection and a transmission, and not just in one direction. So the light, for example, say of this boundary here, that's reflecting this way, hits this boundary and reflects back again. And it's just constantly reflecting and transmitting in both directions. And how the filter blocks unwanted light is you very carefully select the thickness of these layers. And if you make the layers so that they are on the order of a quarter of the wavelength of the pass band you want to keep, then that wavelength of light, all of the reflections end up in phase with each other, and they all add up again on the other side with virtually no loss. It's kind of a clever way of doing it. It depends on the wave properties of light. By keeping all of the reflections in phase with each other, you end up allowing that light to kind of sum up at the end and be unattenuated. But if the light is of a different wavelength than what you've designed the filter for, all of the reflections are out of phase. And so when you add all the reflections up, they cancel each other out. So it's a very clever way of tuning the filter to pass specifically what you want. It also means that these filters are quite expensive. The technology to do this was only available since maybe the 1980s. And it's getting gradually more affordable, but they're still the most expensive filters that you would buy would be a filter made with this type of technology. So now that you've all kind of glazed over talking about wave properties of light, we'll talk about some general nomenclature for describing how a filter behaves. And this is information that I'll hopefully convey and you'll remember for next time, because it's going to be relevant to our talk about what filters you want to use and what filters you don't want to use in our second part. So this is a typical plot of how a filter responds to different wavelengths of light. So across the bottom is the wavelength, going from 400 to 700. That's basically the visible range of the spectrum. And the transmission here as a percentage on the left side, from 0 to 100. So this particular filter is called a low-pass filter. So everything that is on the low wavelength side of the cutoff is being passed, and everything on the high side is being blocked. The point where the transmission is half of the maximum. This maximum is about 90% as drawn here, so half of that is 45%. So that point there at the halfway point is what the cutoff wavelength is denoted by. So in this case, it's about 550 nanometer low-pass filter, is how I would describe this. The same is true on the other side. A high-pass filter, you describe the cutoff wavelength the same way. The difference is a high-pass means that everything on the high side of the cutoff gets passed and everything on the low side gets rejected. We combine these two, you get what we call a band-pass filter. So you have two cutoff wavelengths, one on the low side, one on the high side, and then everything in between is what the filter is allowing to pass through. The wavelength difference here between the two cutoffs is what is called the full width half maximum bandwidth. In this case, it's about 90 nanometers wide. The center wavelength is, as you might expect, it's the midway point between the two cutoffs. And in this case, the filter's in-band transmission is on the order of 90%. So that's a generic look at what a bandpass filter response looks like. And this will make more sense when we look at some real filters that you would use next time. So this guy here I would call a wide bandpass. 90 nanometers is pretty wide. There are things that exist called narrow bandpass filters. These would be typically used for astrophotography, where you want to just image one particular wavelength coming from an object. Also, observing the sun is a good example. In hydrogen alpha, that is an extremely narrow band filter. The width here, the full width half maximum, is fractions of a nanometer wide. You can also have filters that give you more than one passband. In this case, 2 or a dual band. You can also have tri-band or quad band. And you can even go crazy and have something called a multi-band pass filter. Or some people call it a multi-band block filter. So this is kind of an idea of how filter responses can look. The last nomenclature to go over, it's a little bit technical, but hopefully we can get through it together. There's a general term used to describe how dark a filter is. And it's called the luminous transmissivity. It's a percentage, 0 to 100, of how much light is getting through the filter. And if anybody already has color filters in their observation kits, there might be a percentage written on the side. This is the value of luminous transmissivity. Now, the thing is, this value, the number itself, depends on what is doing the observing. So the transmission of the filter as viewed by your eye is different than if you view with a camera or with some other type of sensor. So the number that is on the filter that you buy in a store is only relevant to whatever they used to measure the filter's transmission with. And this is something that people who sell the filters don't tell you. And it just happens because all the color filters sold today are based on the Ratten system. The luminous transmissivity number that you get quoted is daytime visual use. So your eye, spectral response during the daytime, how dark the filter looks, which is completely useless because we're trying to use these filters in the dark. So it's just a heads up for you. Anybody who wants to know how you calculate this number, you can come see me after, but here's the math. It's a weighted average. If this is the filter response, you take the average of this over the wavelength range that you're interested in, but you weight it by the response of the sensor. So it's not a complicated calculation, but it's kind of boring. So if you want to know more, you can come see me about it. So a few last words. Tonight I've just given you a really brief introduction to filters. So how they work, why they work, the nuts and bolts of how you're actually able to take advantage of these. I'm going to cover, like I said, in part 2, where I'll talk about filters that I use, and I have tested quite a few filters in my day, as Simon and Jim can attest. So I have a good idea of what filters you probably want to have in your kit, and which ones you can just ignore. But we'll cover that next time. And that's it. Thank you. I'll stand for questions. All right, I guess over here.
Yes, okay. Thank you for your presentation. You mentioned earlier on in the presentation that these filters are geared to cameras and also telescope eyepieces, correct?
That's correct, yeah.
Why don't they have anything for binoculars?
They do, actually. If you have, there are some brands of binoculars that have a 2-inch thread on the end. Yeah. And you can put 2-inch diameter astronomical filters on the binoculars.
On the inside of the
On the objective area.
Okay.
Yeah.
Some also go on eyepieces.
Yes, if you have binoculars that you can change the eyepieces, you can put an 1.25 inch on the end of those.
And what would you suggest for, let's say, a moon filter for binoculars? When you see a full moon, the white light, for myself, it bothers my eyes.
It's too bright, too intense.
Of course, yeah. But I would think a green filter would work out perfect.
if you don't mind the tint that would then be applied to the moon, some people don't like the shading that you get, because you can also use different colored filters to accentuate different features. But then the whole moon looks, as you suggest, it would look green if you use the green filter. There is something called the variable polarizing filter, which is very useful because it's two linear polarizing filters that you can adjust their angle to each other, and by doing so, you vary how much it darkens the view. It's like a variable darkening filter. So that may be something that you can investigate.
Maybe in a similar way to the two processes that you were describing this evening?
The polarizing filter? It's it's exactly the same as a color filter. It's a gel sandwiched between two pieces of glass. I don't know how you make a polarizing film. They've been doing it for a long time, but it's essentially a thin plastic layer that's sandwiched between two layers of glass. So that also makes them vulnerable to getting moisture and ingress in the edges. So you have to be careful with them. Yeah, the red jacket.
Yeah, so we also know what type of telescope we're using too. We should say an achromat, we're using different techniques. I've got a filter than Apple Chromat or quick acid. Depending on the light beam translated to, when you go to achromat, you're not getting any focus on the same plane. In an Apple, we will, so you can get away, you need a better filter to get the same result in an achromat than you will in an Apple, with an Apple.
Yeah, it kind of depends on what you're aiming to achieve.
Say you're doing lunar planetary.
Like, yeah, say you're doing lunar planetary and you're trying to A, improve the contrast of what you're trying to look at, but also B, trying to eliminate the purple fringe that you get, the chromatic aberration, then yeah, you can get filters that specifically remove that, as well as improve the contrast. I can make some suggestions if you want, filters that do that. I know a few that do that. Any other questions?
Jim, when did they switch over from dyed glass to the gel sandwich?
Actually, it's the other way around. They were always gels in the beginning. It stems from terrestrial photography. If you know anybody who's really into serious photography, all of their light color correction filters that they use are typically gels. They're like 4x4. And that stems from the technology that was used to make these originally. That they were made using, I can't remember what it's like a naturally occurring plastic viscose or something like that. It's a celluloid, like naturally occurring clear plastic materials were used initially with dye infused. And it wasn't until probably the last couple of decades that you start seeing actual dye-infused glass. And a lot of this still has to do with the cost. It's much cheaper to make rolls and rolls of dyed gel and then cut it up and sandwich it between glass than to try to get a uniform dye infusion in the glass process. Any other questions?
Yeah.
Yeah, way over there.
How important is it for the glass that forms the sandwich to be plain, perfectly plain? Is that a significant difference?
It is, actually. Certainly for planetary, I would say it's important. If you're doing narrowband work, that's more of an imaging issue. You also need to have all the surfaces have to be planar, or else you're going to get halos because of the reflections not being aligned with each other as they pass through the various layers. So it is important, and that is a good reason why for filters, and we'll talk about this next time, thank you for the survey, it does pay to buy expensive filters. Because the cheap ones that you find online, they have issues like this, where the glass they're using is not planar, and you can get halos and other imaging effects.
See,
covering enough time. I'll give a nice little lookup table of
One more question.
recommendations.
Any more?
Anyone?
Yeah.
Yes.
You mentioned the specialty filters. Are you going to talk about them at all? Things like chromatic aberration filters and others. Will you be talking about them next time? Or?
I hadn't planned on it, but if there is enough interest, I can make a part 3. That's possible.
Well, you should put in the long pass, the batter long pass, 495, yellow. It's very good for chromatic aberration.
It is, but there are.
But you can also use a number of ways. Something that's pretty close.
That's an inexpensive solution, but yeah, if by a show of hands, is there interest in a part 3 special filters? Okay, make it so.
It's good for me. One more slot fill.
Okay, we're going to move on to our observation reports for this evening. And again, if you have pictures you wish to submit, please get them into us. Sooner the better. It helps Chris when he builds the slideshow. So tonight we have Hugo, Jim, and Brian. So if you can line up, please.
There you go.
I don't know how well I can see that.
Oh, well.
But I was struck, I was going for breakfast at IKEA on Friday the 20th in the morning. And when I made a turn off the Queensway, I could see outside my side window this rainbow in the sky, and the sky was perfectly clear. And I said, what the heck's going on? But all I could see is that one side, and it was much brighter than what you see there. So when I got out of the car, parked in the IKEA parking lot, first of all, I had fears that my battery had died on my cell phone, which is usually the case. Fortunately, it hadn't died quite, so I whipped it out, and then I had to look for a spot where the sun would be blocked out, because otherwise the sun would totally overexpose the whole thing and I wouldn't get anything. In retrospect, I think I might have been able to find a stop sign, which might have been more appropriate. But it was so cold that morning, my fingers were freezing. So I was very quick, and also I wasn't quite sure how long the phenomenon would last. Anyway, this phenomenon is known as sundogs. So you see more or less like a sun on each side of the regular sun. And in this particular image, you don't see, there's also a slightly brighter spot right on top. So there are actually 3. But what really impressed me, and you don't see that as much in the picture, was that was almost like a really bright rainbow when I first saw it. Here the colors are kind of smudged, but it was very, very bright. And of course, there wasn't a cloud in the sky, so you know what's going on. Anyway, apparently this happens when there are ice crystals up in the upper atmosphere, hexagonal ones, that are parallel to the Earth. And so around a 22-degree arc around the sun, you get these reflections. And this particular one lasted actually halfway through the breakfast, so I could see it out through the window. But like I said, it was so cold, and the most convenient spot where I could block out the sun was the Corvette store there, and that's what I got. Okay.
Thank you. Well done.
Well, good evening, everyone. Happy New Year. Exactly. So we can get some light here. So I'm going to be showing you some images that I took off my balcony, just a few blocks away from here, using a light pollution filter that Jim introduced me to. And this is called the Optilone L-Enhanced filter, which blocks or attenuates city light pollution while isolating hydrogen alpha, beta, and oxygen-free emission lines. So this filter was really, really nice for nebulas. So the good news is that astrophotography is alive and well in the city with a good camera and a good filter. And even though a dark sky is definitely much better, it's kind of nice to know that you can enjoy the hobby right here in the city. So the first image I have is the Dumbbell Nebula. And I took this with my Celestron 8-inch Smith-Cassegrain evolution mount using the Mellencamp Sky Radar with a focal reducer. So it yields approximately an F ratio of F5. And this is a 25-second exposure, a live stack of 10 frames. All right. So the next one, very familiar to all of you, I'm sure, is the Orion Nebula. And I took this with a Williams Optics 8mm refractor at f5.9 with a Mellencamp Sky Radar. No focal reducer was used on the camera. And what I did, I attempted to vary the exposure from 1 second to 5 seconds in order to, while stacking, in order to capture the trapezium in the end, which obviously didn't materialize. But nevertheless, I'm kind of exploring ways of getting maybe some of the low exposure frames to be more representative of the total number of frames that are stacked. And when you do that, you can actually get a little bit more detail, which I didn't accomplish here, but I'm still practicing. And so I got really absorbed, or really enchanted with the detail, and in the process, rotation set in, as you can see. But nevertheless, it was kind of cool. What you see in the upper left-hand corner is the Running Man Nebula in a very faint way. Let's see if I can. The top one. All right. So the Running Man Nebula would be right here. Quite faint, but nevertheless. Okay. So the last image that I'd like to show you, excuse me. Oh, by the way, I'll let you know what the specs are on this. Yeah, it's 1 to 5 seconds. Ultimately, I went with stacking 50 frames, and obviously a bit too long. We get some rotation, but anyway, I'm kind of pleased with that. The last image I'd like to show you is the Crab Nebula, and this is a supernova remnant. I took the Celestron 8-inch Smith-Cassegrain with the Mellencamp and a focal reducer to take this shot. And this is a 26-second exposure, a live stack of 28 frames. And I was really pleased with the clarity of the filament structure here. All of the images that I'm showing you, I did some light post-processing, just manipulating the contrast and the brightness and using some tools to try to cut down on the noise. I really had a lot of fun, and I encourage you all to get involved in astrophotography, and you don't really have to travel very long with the right filter and camera. Thank you very much.
So the first couple of images were from an observing session around the middle of November. It's one of the rare occurrences of a clear night in the Hanmer area this winter. So this was from my backyard in Alta Vista area. I think the sky magnitude is around 2.5, plus 2.5. It's not very good. So I was using a hydrogen alpha filter this evening, 7 nanometer wide, to really cut out the light pollution and only let me see the nebulosity. So this is, as we saw previously in Jim's presentation, the Crab Nebula, SCA number 1. It was taken using a 10-inch Richard Kretchen scope and Skyraider DS432 camera. And I believe it was a 20-second sub-exposures, around 45 of them stacked. So about 15 minutes worth of data collection. This is the Pac-Man Nebula. I don't know if you can see his shape here. So this is his mouth, his eye. He's gobbling ghosts in the downward direction. So this is a lovely emission nebula in Cassiopeia. NGC 281 is the designation. And I was really impressed with how well the hydrogen alpha was able to cut through the light pollution and pull out a lot of really subtle details. I don't know if you can visualize the way I see it, but if you see this circle as an open bowl facing you, and the star cluster is in the center of the bowl, and then on top of the bowl, in between us and the star cluster, is this remaining dust and gas that's being, in the process of being pushed away by the young stars that are in the center of this cluster. And you can even see on the edge of the bowl here the shock wave of the solar, the pushing, the solar wind, thank you very much, pushing back the envelope of hydrogen gas and dust. So I thought that that really came out quite nice. And again, that's 20-second sub-exposures, about 45 or 50 of them stacked, about 15 minutes. The third one is another object that's in Cassiopeia. It's called the Bubble Nebula, NGC 7625, I think. And again, the hydrogen alpha filter really came through again for this object. I believe, I can't remember if this is the star or is it this the star. It's emitting this increased envelope of gas, but because the gas density varies depending on where in the nebula you are, the star is off center from the bubble. Yeah, very, very beautiful object, very delicate structure in the middle of the bubble here, and also some other details, another shock front here that I haven't really seen before I captured this image, so I was quite pleased with that. Later in the evening, so the moon was coming up this whole time. So by the time the moon was at the meridian, I kind of shut down the deep sky and did some lunar imaging. So this is the Altai region, which is sort of the outer edge of a large impact basin, the Nectaris Basin. The center of the basin is kind of over here. But the really low sun angle on that particular night, I thought pulled out the detail of the star quite nicely. And I think, wasn't the crater that you talked about down here? The one that you wanted us to name? Because I think this crater chain here was kind of a strange coincidence.
Yeah, sit down there.
What do you do for seeing? You don't have any seeing.
Yeah.
Well, this is in a single frame. This is the best 10% of 2,000 frames. Stacked using Auto Stacker 3, and then wavelet applied.
And exposure time was?
Let's sub-exposures were fractions of a millisecond. So this is the same 10-inch scope, but made of f8. The whole idea of lucky imaging, I can also talk about if there's desire. Try not to pander to my own. So yeah, I was quite pleased with that, and also the nice detail that came out on the three craters here: Theophilus, Cyrillus, and Catarina. So yeah, that came out quite nice. And then the next little image is in honor of the 50th anniversary of the lunar landing, Apollo 11. So along the same terminator that night, I just happened to take out a nice photo of the area where Tranquility Base is located. On my screen at home with the brighter gamma, you can also pick out the three craters that they named after the three astronauts after the fact. Armstrong, Collins, and Aldrin. But yeah, that was also not a bad capture. Lots of detail in the wrinkle ridges in Sea of Tranquility, and some arenas down here. Kind of nice. So the whole idea of lucky imaging, this is segueing into my next image. The idea is that if you take a lot of pictures, at least one of them is going to be good.
Not the way I do it.
If you're lucky. Especially lucky imaging. And so these two lunar images, as I mentioned, I captured 2,000 frames as a video file, and then use software to sort and pick out the best 10%. Sometimes I use more, sometimes I use less. It depends on the seeing conditions. This evening, the seeing was average for Ottawa, which is pretty crappy. But I wondered to myself, and now aloud, what if I try to apply the same technique to a deep sky object? And my fairly recent purchase of the 432 camera from Cam provided an opportunity to explore this idea. So this is a picture taken using my DS432, using my 10-inch RC, but with a 2x Barlow. So this is f16 with a dual band filter on it, because I wanted to get both oxygen 3 and hydrogen alpha. But it's a 1-second exposure, single frame. Now, I captured about 2,000 of these. Which isn't that long, 2,000 times 1 second. It didn't take too long. And then I stacked the best 500, and I got this. So the noise has been all smoothed out. I'm not sure why my stars have a slight triangular shape. I think I have a combination issue, but I won't worry about that. But this is what you get when you stack a whole bunch of images. And then if you pass it through a sharpening process that we call wavebits, it's a particular type of sharpening routine. It works great on the moon and the planets, but it also works quite well on deep sky objects. So this is the result of passing it through the same process that I did for those earlier moonshots. So there you go. And that's the trapezium that Jim was mentioning. Yeah, so I think that turned out to be a pretty successful experiment. Thank you.
Hi everybody, Happy New Year.
Happy New Year.
Oh, never mind. Okay, it's a new year. Some people would say, yeah, it's a new decade. Some people would say, no, it's not a new decade yet. Not for another year. But never mind all that. There's a new illumination underway. Right? Did anybody see the moon before they were dashing into the meeting tonight?
Nope.
So you have to look up. So we're approaching first quarter moon. Anyway, so we'll just go to the next one here. Oh, all right. One of the lunar challenges was Crater Atlas. And so this is a sketch that I had done, just a quickie sketch back in 2005. So I was getting myself back into doing some more of this, so I went searching that one out. All right, so we've got the craters. Normally they're paired. If you're observing one,
you're observing either Atlas and Hercules. And if you're getting some good seeing and not stacking images, you're getting really good seeing. I really like the way you did those, Jim. It's a nice presentation on those. You can start to see a lot of detail on the floors of these two craters. But what you can especially want to look for is some fracturing in the floor of the Atlas like this. And also there's the central region of it doesn't have it's not a central peak, but it has a central ring, which got me thinking, Simon, when you were doing your talk, about, when craters flood up and they slump a little bit and what's left, and you're trying to figure out, is this probably, I've got a couple of the features here, but there's more of a ring of features. Is that the result of after there was a bit of a central uplift and the whole thing then slumped in the center again? You're going to see slumping along the walls called terracing, and you can get the same thing on Hercules. And you have a Hercules A, which is right in the center of it here, which is quite a prominent crater to look at. Okay, so we'll go to the next one and just show you where we're looking. So if you can look through the wires for some of you, okay? So we're in the upper right quadrant of the moon. So this would be as you step outside and look to the moon, right is right, up is up. So that's the area that we're looking. But I'll just mention one thing. Simon had mentioned the cookie cutter craters, and he used the lunar crater Maurolycus, which is just down right here. All right, and this is also down. This is where Jim was talking about the Altai Scarp coming from the Neptaris Basin. So this is where you're going to see the crater in Nebula. I forgot. That's the one. Yeah, you're faking it too. All right? But anyway, so where the moon is now, it's just outside, for real, it's just approaching first quarter. So it's about the same type of view. So you have a chance to see everything we've been talking about tonight, and even things that Simon was talking about on Venus, with his moon analogy, to be able to see, and Sunday night. I think Sunday might be a bit clearer. Okay? So we have the Sea of Serenity. This is the Sea of Tranquility here. And of course, this is where Jim was showing us the Apollo 11 landing area. And he was showing the view basically from this direction, though, because we were seeing the line of the three craters named after the Apollo 11 astronauts, the two landers and the one orbiter astronaut. And in the left of his view, in the lower left of his view, was the crater Julius Caesar, which is right here. Right? So, Sea of Serenity. And you have a little inlet going in here, and you can see it over on the map off to the right. But number 35 here on this map is the crater Posidonis. And that's a beautiful, beautiful crater to observe. But that's your gateway. This is your gateway in. So what I'm going to do is I'm going to go to the next slide. Yes. And what I've done is I've flipped my sketch. Because the telescope I was using at the time, and or the combination of eyepieces, whatever, I had a flipped view. So I've flipped everything now, so it matches the same order. So there's Hercules there, and Atlas. There's Hercules and Atlas. And we come down, we'll see the crater Cepheus here, and the crater Franklin. And this is actually Cepheus here, and Franklin down here. Yeah, so not all the detail shows here, and certainly not all the detail shows up in that view here. But I just wanted to match them up. I had done a presentation a number of years ago on Cepheus. This is Greater Cepheus. And it looked like a hippie with shades on, with long black hair tied back down here. There's his nose. His nose has got this, hey man, shades on, all right? Very interesting region to look at, but as you go through from the Sea of Serenity and you go in through here, there's a whole world to explore. And what's really of interest, I've taken a couple of charts from Antonin Ruppel's Atlas of the Moon, charts 14 and 15. Thank you very much. And as we're coming in from the Sea of Serenity down this way, with crater Posidonis down here, you can come in, the first thing you get is to the Lake of Dreams, Lacus Somniorum. It's the largest of the 20 lakes on the moon. It's about just under 400 kilometers in diameter. And just north of it, Lacus Mortis, right, the Lake of Death, which is about 150 or so kilometers across, and it's got this great crater Berg in the middle, and that's a really interesting target to look at. So now we cut across, and we can see Hercules with its huge crater. Of course, that was an impact that happened after the main crater had formed. And then we go across to Atlas down here, get down to Cepheus, and down to Franklin. So it's all very interesting on here. The one thing that I really enjoyed when I was doing my sketch here was the crater details, but then you see these a shore here, this jagged shore. And all you get from and I have to look to see, it's not really identified that I found as a specific feature, other than labeled as there's this close crater to it, N, probably coming off of, I don't know if you're, sorry, I don't know if this is the N off Franklin or if this is the N off Atlas. I think it's off Franklin. I have to do a bit more investigation. I wasn't looking too deeply at that time before we came down. Just off to the right, though, just interestingly, is the Lake of Time. So you have the Lake of Dreams, Lake of Death, Lake of Time off to the right. So now we're going to do a little tricky thing. I'm going to marry my sketch with the view here. And I was debating on how fast I should make this transition so I could see either how nifty I had done things, or how bad my sketch was compared to what the thing was. But we'll go here. So it did a bit quicker transition than I had set up, I thought, but I'll back it up again. So there it is there. Oh, I thought it would peel away. Okay. And so here you see one of the problems when we're doing sketching, and we talked about that when we did the sketching workshop, right? And we talked about sometimes the scale of things might not be exact, and that takes practice. And also, when you're working up in the northeast of the moon there, you're working toward the limb. So as things are folding away, you're starting to get a foreshortened view. So sometimes you cheat, and your brain is cheating, saying, well, if that's a crater, it's round, and you draw it round, and like I did on one not too long ago, and I had to go and shift it in Photoshop to, no, it was actually, it's squashed. And that's the things to look for, and that's part of the fun. One thing you can use your Observer's Handbook, if you are a member, and get your Observer's Handbook, is that it will show you there on the positions of the moon, it'll show a dot, or in your I think in the calendar it shows that with the moon positions, it'll show a dot on one of the corners of the moon, a red dot. The red dot is showing the libration. And the libration is the moon kind of wibbles and wobbles as it goes around, and so sometimes we see a bit more tipped towards us, sometimes it's tipped away from us. So what you want to do is find an image of the moon that or a time when the moon has got that part tipped towards us, librated toward us, and then you get a much clearer view. But it's a very exciting, very interesting place to observe, and you can spend a lot of time in there. And while you're sketching the actual details, don't forget to play with your imagination. Enjoy your little trip there. Thank you.
Well, this was last month's observation challenges. Hopefully some of you were able to do that, and if you capture pictures of them, that would be awesome as well. Send them in for the observations. If you can't get them ready in time for the upcoming meeting, that's not an issue. We'll take observations anytime. So I talked to Oscar, and he's been willing to continue to pull together the challenge. I don't think Oscar's here tonight, though, is he? No. No. Okay, so these are the challenges that he has put forward for you for this upcoming month. So we've got Messier 34 as the beginner challenge, NGC 1501 as the intermediate challenge. And I'm going through these fairly quickly, but they will be in the astronauts, right, Gordon? Yes. Okay, so the advanced challenge is NGC 1232A. And your lunar challenge are Frederius and Fraunhofer. So those are the two craters to look for.
I love the names. I like it.
So there's a summary of the challenges for the upcoming month. Hopefully we'll have no cloudy skies. Estelle's pick of the month. We have a library back here and behind the curtains, and you're welcome to go back there. Our pick of the month is Mars Spirit Opportunity and Exploration of the Red Planet, and members are welcome to sign books out of the library. These are the various contact people within the club if you have questions about these various things. We had 123 out, which is great for Friday just after New Year's. Thank you for all the people who have contributed here this evening, and to special thanks to the Canadian Aviation and Space Museum. The post-meeting entertainment is at Grace O'Malley's. Just go up to the end of the parkway, hang a right on Ogilvy. It's on the right-hand side there. Our next meeting is February the 7th, 7:30 p.m. I'm still working on confirming some of the speakers, but it looks like it's going to be a really interesting meeting. If you have any ideas, please email me, meetingchair@rasc ottawa.rasc.ca. And thank you to everybody who's already sent me a pile of suggestions. I'm working on them. And I mean, as I said, mentioned in my email, I may tap you on the shoulder at some point to help me out with those. Membership. So if you wish to become a member of the Royal Astronomical Society, a regular membership is $86. A family membership is $80 plus $13 per adult and $7.10 per youth. And youth membership under 21 years old or under 25 if you're a student is $52 a year. With your membership, you get access to the Ted Bean Loan Library, so you can borrow telescopes. You have access to, some of the people talk about FLOW, that's the Fred Glossing Observatory, which is out near Almont, and you have access to that. You have access to the library. And from National, you get Sky News, the Journal, the Observer's Handbook. You get a free version of that every year. And we have our own Astronauts, which is an awesome magazine that comes out monthly. Gordon Webster is the editor of that. So we're going to move into the